My name is Dan Vandebunty, and I'm not a popular YouTuber. I don't mean to say that I am particularly unpopular, but you've probably never heard of me. The mathematics that I am about to present is not something that is generally out there in the world, as far as I know anyway. It's a problem I began working on in high school and have been working on ever since. As far as I know, I am the only one who has ever worked on this particular problem, and I do not know of any practical applications for this problem. But it's my problem. This is personal for me, and that's the point. At its core, this video is about the journey we go on when solving a complex problem like this. And this problem did take me on a journey from high school geometry all the way to Galois theory, with several stops along the way. The journey began in my high school geometry class. In high school, most of us learn that when you drop the perpendicular from the right angle of a right triangle to the hypotenuse, that you create three similar triangles. The two right triangles created by the perpendicular and the original right triangle are all similar. After learning this in high school, I asked myself what I thought was a natural question to ask. Will the two created triangles ever be congruent to each other? And if you think about it, you can probably determine that yes, there is one case for which the two created triangles will be congruent, and it's fairly obvious once you realize what it is. But most of the time they won't be. So that turned out to be a pretty silly question with a fairly easy solution. The question was barely worth asking, so I tweaked it. What if we keep dropping new perpendiculars, as illustrated? Then can we get congruent triangles? If so, when? If not, why not? Can we get congruent triangles with the second perpendicular, the third? Can we get them for arbitrarily large numbers of perpendiculars? In this diagram, will triangle A, dn-1, dn ever be congruent to triangle CBD1? If so, for what value of theta? We'll call that value theta n. Once I learned about trigonometry, which was probably in the same geometry class, it seemed like the next logical stop on the journey. It's natural to suggest that because this problem relies heavily on right triangles, that expressing it as a trigonometry problem could be beneficial. I figured that I could just assume that the original hypotenuse has length 1, common practice in trigonometry, and everything else could be expressed in terms of sine theta n and cosine theta n. Doing so allowed me to express two corresponding segments in terms of trigonometric ratios. If the two segments had the same length, the two triangles would be congruent. For the angle theta n shown, the side opposite theta n, that is dn-1 dn, will have length cosine to the n theta n times sine theta n, while side B d1 has length sine squared theta n. That allowed me to work with a new equation and simplify it a bit. Since the only feasible value of theta n for which sine theta n would be 0 is 0, and that does not produce a triangle at all, we can divide both sides by sine theta n to simplify, and this yields a simpler equation. Well, somewhat simpler. Squaring both sides allowed me to make use of a well-known identity and rewrite the equation in terms of only cosines. After some more rewriting, I got another equation. Only this new equation looked a lot like a polynomial. At this point, it was time to say farewell to expressing this problem in terms of trigonometry and make my way to algebra. Making a straightforward substitution of defining x to be the square of cosine theta n yielded a fairly simple looking polynomial structure for the problem. A new form of the equation meant I now had access to new mathematical tools. The problem turned into a question about zeros of polynomials, and we have a bunch of ways to find those. The case for n equals 1 is easy enough to solve, as you can see. And after working with it a little, I got a theta value of pi fourths, which is equivalent to 45 degrees. And when you think about it, when you draw the perpendicular from the right angle of a 45, 45, 90 triangle to the hypotenuse, you do in fact get two new triangles, which are congruent to each other. The case for n equals 2 perpendiculars translates into a quadratic equation, which we can solve using the quadratic formula. And from that solution, we can work backwards to identify the corresponding value of theta n. Now we are cooking with fire. The case for n equals 3 produces a cubic polynomial, and we have a formula for solutions to cubic equations. I've put that solution up, but I won't bore you by trying to read it out. In any event, we can reverse engineer the corresponding theta n for this case as well. The case for n equals 4 produces a quartic equation, and we have a formula for solutions to quartic equations. In this case, the solutions are not pretty at all. See? If you're trying to read this, you might want to pause the video. But whatever, we can still identify the solutions. The corresponding theta for n equals 4 is just the inverse cosine of the square root of that whole messy thing. Well, the positive version of that whole messy thing. Unfortunately, after several years of making no progress at all, the journey made an unexpected stop in Galois theory. After I got stuck, I resorted to posting my problem in an online forum and hoping that someone could help me. And someone did, just not in the way I was hoping. Galois group? What? I had no idea how to proceed. I looked up what a Galois group was, but immediately recognized that it was beyond my education up to that point. And this led to a long, I'll call it a sabbatical, from working on the problem. This was around 2002. Fast forward 20 years. The last class I had to take for my master's degree was a survey of algebra class in which we would, near the end of the term, be studying Galois theory. As luck would have it, we also had to submit a final project at the end of the class about something we had studied in class. I knew what my project would be the moment I read the syllabus. It wasn't until I was working on my final project that I realized making a quick trip to calculus would provide some much needed perspective. Personal confession time. I feel silly for missing this earlier, but one of the things I did in my project was based on calculus concepts that I had been teaching for years. When I saw the connection, I was quickly able to make a giant step in solving the problem. Well, sort of. The function I was using was a polynomial, and polynomials are continuous. Combine that with some basic information about my polynomial specifically, and boom! Existence theorem. The y-intercept was always -1. The polynomial always contained the point 1, 1. And by the intermediate value theorem, there would always be a positive x-intercept between 0 and 1. Always! No matter what n you choose, there is a right triangle that will produce two congruent triangles with the nth perpendicular. So even though I knew there would always be a solution, this journey was destined to end back in Galois theory. Yes, there will be a solution, but don't expect to find its exact value. Thinking back to the response I got online, I wondered why n being congruent to 5 mod 6 made any difference at all. So I consulted Wolfram Alpha to analyze the solutions for n equals 5, 11, and 17. I found that each of the associated polynomials had the same quadratic factor. I proved this result in my project using induction, but I'll just share the result here. If n is congruent to 5 mod 6, x squared minus x plus 1 is a factor of x to the n plus x minus 1, my polynomial. So the case for n equals 5 shouldn't be solvable, but it is. Using the known quadratic factor for the case when n equals 5, the problem reduces to finding the zeros of a cubic function, which we have formulas for. But this only works because the other factor turned out to be cubic. You can see the resulting solution on the screen. If n equals 11, the remaining factor will have degree 9. And then Galois theory really does slam the door on you. In the end, I was able to prove that this problem has a solution for any positive integer n. But because of Galois theory, I had to give up hope of trying to find some formula or pattern that would find the solution for any given n, which is originally what I was hoping for all those years ago. Over the span of 30 years, this problem took me on a journey from geometry to trigonometry to algebra to Galois theory to calculus and back to Galois theory. All because of a question I thought was fairly simple in my youth. A question that originally had an intuitive solution. And a question that became far more interesting by tweaking it just a bit. Does that mean I can add chaos theory to the list? In any event, thank you for allowing me to share this with you.